Hi, I'm Jeongyeon, and I'm glad to share our work, FitVid, responsive and flexible video content adaptation. According to the growth of mobile learning, educational websites and textual learning materials are rendered responsibly on various mobile devices. Then how about the video content? They are simply embedded in different screens. In particular, content-heavy materials such as video lectures contain dense text and small graphics to digest on small screens. This indicates a need for responsive content adaptation of video content, which is, however, challenging for multiple reasons. First, we need to decompose video into design elements such as text and images to resize and rearrange them to fit small screen sizes. However, the semantic information in videos is buried in pixels and becomes a sequence of frames. Although the existing research used a non-pixel-based approach to extract metadata, access to the lecture slides is often limited. Furthermore, video lectures involve dynamic elements such as talking head instructors and real-time handwritings, which are not included in the lecture slides. Second, a high diversity of lecture designs makes the content adaptation even harder. Although there have been attempts to adapt the video content by using rule-based methods, creating heuristic rules include massive manual work and consideration for the combinatorial explosion of possible conditions. Considering those challenges of the non-pixel-based approach and rule-based methods, we designed a system that automatically adapts and customizes video content designed for desktop environments to small mobile screens, making it more readable and digestible. The computational pipeline of our system consists of three main parts, which analyzes the static objects and the dynamic objects, and then maps the on-screen text to audio narrations. To generate the content adaptation, it is essential to locate and identify the in-video elements, to resize and rearrange them for the adaptation. The decomposition module extracts the metadata of the in-video elements from raw pixels by leveraging the deep learning techniques. To train the object detection models, we collected and annotated 5527 lecture video frames and trained a custom object detection model to classify lecture design elements. Another characteristic of video lectures is that they contain dynamic objects such as talking head instructors and real-time handwritings. To extract those elements, we first detected the movements in the videos and then identified them using the results of static object detection in the previous step. As a next step, we built mappings between the text elements on the screen and the audio narrations to display the decomposed elements at the right timing after the adaptation. So far, we decomposed the video into design elements, and now the adaptation module generates and renders the adapted content by applying existing design guidelines for mobile content. We generate the content adaptations by enlarging the font sizes and reducing the amount of text, changing the column layout to maximize the readability, adjusting both image and text at a compromise point where the average design guideline compliance rate is maximized, increasing the color contrast, and changing the typeface to ensure the readability. However, the pipeline-generated content may sometimes produce incorrect adaptations and may not satisfy every user's needs. Thus, FitVid provides users control over the content adaptation instead of automating the whole process. Users can directly manipulate the in-video elements extracted using the reverse engineering approach by resizing and repositioning to recover the automation's deficient results. And they can further customize the content using design options, toggling the talking head instructors. And they can also turn on and off the slide templates, such as university logos, to optimize mobile screen space. And lastly, our system supports dark mode option. We demonstrated the effectiveness of FitVid through quantitative pipeline evaluation and empirical user study. Our adaptation pipeline increases the guideline compliance rate of design elements by 24%, 8%, and 4% of each main design elements. We also asked 198 participants who were recruited on mTurk to evaluate the content adaptation results. The content adaptation study shows that the adaptation significantly increases the perceived readability and design satisfaction. The user study indicates that FitVid significantly improves the learning experience with increased readability. For example, one participant mentioned that the original content was painful to watch, while the adapted one was readable. They also expressed their preference for the content customization feature. One participant stated that he felt like he has more control over his learning because he could adjust the content in his own way. We also have identified 3 types of motivations for direct manipulation. First, participants use direct manipulation to adjust the design. For example, they resize the elements for better readability. They noted that the direct manipulation allows them further customize the automated adaptation results. The second motivation was to promote concentration. They used direct manipulation to put away the content they finished watching or highlight important parts. Lastly, it was used to interact with content. Several participants enjoyed the feeling of interaction itself and used it without pragmatic goals. They expressed excitement about the interactivity. We also suggest design implications for responsive and customized video content design. First, the responsive design for various display settings. Although our work mainly focused on mobile phone displays, its pipeline can also support large screen or multi-screen settings. Or future work can adapt content to fit even smaller screens, such as smartwatches. During the user study, the participants didn't show full trust in the automated adaptation results, checking if any necessary content is missing after the adaptation. For this reason, they appreciated the feature that allows them to access the original content without the adaptation. This is in line with the human-AI interaction design guidelines, suggesting that the system should provide easy correction and controls over the automated results. Future work can provide options to learners to choose the degree of adaptation from minor adjustments to aggressive adaptation. We could observe that the direct manipulation feature allows learners to adjust and customize the automated adaptation results. The adaptation techniques can evolve to be more personalized by leveraging the manipulation bug. For example, personalizing the default font sizes based on the manipulation bug. I believe that our work can be an initial step towards customized video interfaces through responsive and fluid content adaptation, which enhances the accessibility of video content for users in various contexts and situations.